The first slide is just going back in time to chapter 5. So that's where we were dealing with parameters, whether we knew it or not. And remember, the mean and standard deviation of a population are parameters. For the population mean, we use the Greek letter mu. For the population standard deviation, we use the Greek letter sigma. Remember, x minus mu over sigma equals z, that kind of thing. So an example of something that we would use these parameters with is something like IQ test scores, because they're designed to be normally distributed. They have a mean of 100 and a standard deviation of 15. And we've always mentioned the shorthand notation, but keep in mind that if you're asked to do a complete description of the population of IQ scores, you can just go ahead and just write this little bitty thing in that notation, because that completely describes what we've got. So IQ is capital N with mean of 100 and standard deviation of 15. You don't have to write it all out in words like this. All right, so that's where we were. Here is where we're going. All right, suppose that x bar is the mean of a simple random sample of size n, drawn from a large population with mean mu and standard deviation sigma. All right, remember that the mean of the sampling distribution of x bar is an unbiased estimator of mu for the population. All right, that would be mu of x bar. And if you know one, you know the other, because if they're unbiased, then they're the same. All right? So if I tell you the population mean is 100, you can use that for a population question or a sampling distribution question. Now the standard deviation will change, right? Because if you're going to create distributions of averages of a bunch of things, samples of size n, you're going to remove variation by the simple act of doing those averages, right? So it turns out your standard deviation for your sampling distribution of x bar will be the population standard deviation divided by the square root of n. That'll be your sigma sub x bar, right? You need to know that. We're going to use it. Remember, sampling distribution of x bar is the distribution of all sample means from all possible samples of size n. All right. Just some things. Remember, I just now mentioned that the sample mean x bar is an unbiased estimator of the population mean mu. Values of x bar get less spread out for larger samples. That makes sense, because the more things you average, the more accurate that average gets. All right, this is important because I can see this morphing into a test question or an AP question. All right, your standard deviation for your sampling distribution of x bar decreases at a rate of square root of n, right? Thus, you must take a sample 4 times as large to cut the standard deviation in half. Just think about it. If n is 4, the square root is 2. If you divide by 2, you cut things in half. So if you put a 4 in here, that'll give you a certain spread. If you multiply that 4 times another 4 and you get 16, that'll give you a sampling distribution with half of the spread of the previous. Okay? So quadruple your sample size will cut your standard deviation for your sampling distribution in half. All right, this showed up yesterday. It was a little hard to fathom, but here we'll get a better handle on it. All right, your population must be at least 10 times the sample size to use the formula sigma divided by radical n. That's really this formula right here. All right, so your population has to be substantially bigger than your sample size. Your sample size can be relatively big. Your population just has to be at least 10 times as big. If it's not, then the relationship that allows you to develop the standard deviation of your sampling distribution, that all breaks down. So we need this. Now, if you look at these 4 things, nothing in here says anything about anything being normal. All right? This applies to any distribution, no matter what the shape is in the population. All right? So these are ideas that you need to get a good handle on, and don't worry about them having to start out normal. They don't. We want things to be normal. Don't get me wrong, it makes calculations possible. But just for regular old generic sampling distributions, no matter what their shape, those 4 rules apply. All right, so here, this is just a quick exploration in how variation changes as sample size changes. So if you look at A, these are all possible samples of size 1. Well, anything that's just all possible samples of size 1 is your population, right? Because you look at things individually. In fact, we can say the population is a sampling distribution for all possible samples of size 1, but we don't say that, because if you're just picking things one at a time, that's not really sampling, right? You need kind of more things than just one. But anyway, if you look at this population distribution, it's wildly skewed to the right. If you take all these individuals and pair them up in all possible pairs and say, let's just take a sample average for all of them and throw them into a new distribution, here's your sampling distribution for all possible samples of size 2. Your skew is starting to drop, whereas this would stretch out to the right. Now there's getting a little peak to it, a little mound, right? If you take these all these individuals and then group them by tens and take sample averages for groups of all possible groups of 10, this spread gets even smaller, and this part of your skew begins to collapse. So this is starting to look kind of mound-shaped, isn't it? It's the variability compared to this, it's way less. Now, if you take all these individuals and put them together in all possible groups of 25 and get averages for those groups and make a distribution of that, this is what you would get. All right, this is a pretty big sample size, and your distribution for your sampling distribution is not only decreasing in its spread, like see all the skew to the right, and now there's barely any. This is now becoming to look kind of normal. Like maybe we could do normal calculations on it and get away with it. We'll look at that phenomena in a minute. So that's how variation in your sampling distribution changes as your sample sizes grow. All right, so sampling mean of a sampling distribution of a sample mean, this is critically important. If you take a random sample of any size from a normally distributed population, the key being normally distributed population, your sampling distribution, no matter how big a sample size it's built on, of your sample means will also be normally distributed. All right? What this is saying is if they report to you your original population distribution is normal, you are good to go, whether you're doing population standard normal calculations or the same thing with sampling distributions. Normal populations create normally distributed sampling distributions for sample means. All right? So if you see they tell you things are normal, that's good. All right, so here is population distribution is bell-shaped, but it's really wide because there's a lot of variation as you are looking at each individual observation separately, and that's going to give you the max amount of variation. If you start grouping all of these folks in groups of 10 and taking averages, then you will get this, which is also normally distributed, it's just far less spread apart. So here's sigma for this one, here's sigma for this one, quite a lot longer. The center's still the same, it's just that you're averaging out a lot of that extra variation that you see when you're looking at the population. But normal begets normal. All right, but what if you don't know if something's normal, or if you're told it's not normal, right? If a sample of size n is large enough, and we'll talk about what constitutes large enough, a population with mean, mu, and standard deviation sigma will give a sampling distribution of means which is approximately normal. And don't worry about that approximately like you're almost there, you're just about there. I mean, it's going to be such a good approximation, you can do normal calculations without giving it really a second thought. This is true no matter the shape of the population distribution. and I've got a demonstration, and I'm going to create the craziest population, and the sampling distribution will look nice and bell-shaped, trust me. Now, what constitutes a sample size n that's large enough? Let's all agree that n has to be greater than or equal to 30. Then your central limit theorem applies, and you can do normal calculations on the sampling distribution, even if you couldn't do it on the original population distribution, okay? Now, if you're trying to develop a rationale for using the central limit theorem, or to do normal calculations on a sampling distribution, and your only way of doing it is that your sample size is at 30 or more, you can explain it by saying your sampling distribution is approximately normal. You can say due to the central limit theorem, or the CLT for short. You can say samples are large enough because n is greater than or equal to 30, or n is 45, or something to that effect. Okay? So we're going to actually mandate doing this once we get to inference. All right, here's the demo. Love the demo. This is up online. All right, you click that and just go here to begin. Now, what you see here is a normally distributed population. I know it's all jaggedy, but that's just the graphics. Pretend it's smooth. And let's just say I want a sample size of 5. If I show that being drawn, okay, there are 5 individuals, and there's the average. See how the average tends toward the middle? And you can just do that. There's another group of 5, do it again. There's another group of 5, do it again. There's another group of 5. This is a very slow process. Let's speed it up. Let's do a 10,000 samples of size 5. Oh, check it out. Nice and symmetric and bell-shaped. If you do 100,000, it's even nicer, right? So normal begets normal. It doesn't matter if your sample size is small or if your sample size is big. Watch. Sample size of size 25. It's skinnier than that of 5 because the bigger the sample size, the less variability, but it's nice and symmetric. It's normal, right? Normal begets normal. Okay. What if I go with uniform? That's not normal. That's not bell-shaped. I could do samples of size 5, but I wanted you to see samples of size 25. I know that that's not 30. It's pretty close though. So we'll just pretend that this will give us the central limit theorem. Now if I just let it do it, you know, sample by sample by sample, it's got to drop 25 individuals. See, some are low and some are high, some are in the middle. And see how that thing went right to the middle, right? See all that variation being averaged out? All right, this is going to take forever. I mean, if I did it again, yawn, got to wait for it to drop 25, then average them up. Looks like we'll get close to the middle again if we're lucky. All right, pretty close. All right, we're not going to sit through a bunch of these. This is what it looks like if I do 10,000 samples. Oh, look at that. Approximately normal. There's your central limit theorem. 100,000, even a little better. So if you start out with something that's really non-normal like this, your sampling distribution can still handle normal calculations. So we started uniform. Let's go to skewed. And I'll just go ahead and do 10,000. See that? Even though this is skewed, your sampling distribution is approximately normal. It's nearly normal. All right, and I'm really going to have fun now. I'm going to go back to uniform, and I'm able to just go through this and build my own crazy, crazy, crazy distribution. All right, that is nowhere near normal, right? Let's see if the central limit theorem still works, right? Sample of size 25, going to do 10,000. Oh, looky there. And it's even more so for 100,000. So there's your central limit theorem. It doesn't matter what you start out with, so long as your sample size is sufficiently large, and we're going to go a little bigger than this, your sampling distributions will be normal, and you can do standard normal calculations on them. All right? Good stuff, good times. Don't need to see that. All right, so if you're doing a problem where you have to do a standard normal calculation on a sampling distribution, look to see if they tell you the population's normal. If so, you're good to go. If they don't tell you that, then look to see that your sample size that they reference is at 30 or more, in which case you're good to go. If neither one of those things are true, you can't make them true. You're just going to go ahead and decline to calculate. All right, this law of large numbers, we learned this originally during random variables. Remember, the more you repeat things and average them up, the closer they get to the true value. Well, it's the same thing here. Remember, I was dropping all those samples. If I could keep dropping them more and more and more and more and more and getting an average of them, I'm going to get the true value of the population. This is how we know what the true values of the populations are, because we get at it through sampling. And with repeated sampling, we are going to start zeroing in on the true value. All right, so all of these four things are going to be kind of a recap of what you need to know. All right, for your sampling distribution, these should be equal to the population parameters. They're an unbiased estimator, so if you know mu of x bar, and vice versa. If your population is at least 10 times your sample size, this equation works. So the standard deviation of your sampling distribution is the population standard deviation over the square root of n, so long as this condition holds. Again, if your population is normal, then any sampling distribution you generate from it will also be normal, even if the samples are small, like 2 or 3 or 5 or something like that. If your population is not normal, or if they just don't say, then the sample size must be at least 30 for your central limit theorem to be applied. This will make your sampling distribution approximately normal. All right, so these are your working general properties for when you do your homework. All right, this is your homework, so I'm going to scoot past this. And what you need to do is go to page 6 in your packet. I am going to get a pause going, and I'll be right back. All right, eager learners, I'm back. I just had to set up for this page 6 in your packet. Really, how would you know I did that? Maybe I drove over to La Centera for a delicious beverage. Who would know? But trust me when I tell you, I'm all business. All right, so what we're going to do here is just work problem number 1. And let's see if I can get my pen to work. And problem number 1 has 4 parts. A, B are the old standard normal calculations that we're used to doing. C and D will be the new calculations from sampling distributions. All right. Now, I'm not going to spend a lot of time on this. I'm not going to draw a whole lot of curves. Whatever curves I need, I'll draw them. So I'm not going to be totally complete with what I do, but I think I will communicate pretty well what's going on. So assume that the duration of human pregnancies can be described by a normal model. Okay, that's important, normal model. And it has a mean of 266 days and a standard deviation of 16. They did not mention sampling, all right? So we can make the complete description. This is normal with a mean of 266 and a standard deviation of 16. And let me get a little bit more of a flow here. All right. And so we're in just regular standard normal calculations for populations. No samples have been listed. So remember, we need to end up with z equals x minus mu over sigma. All right? And now they're asking what percentage of pregnancies should last between 270 and 280 days. This is all pregnancies, right? Not just from sampling. So we're kind of looking at where individuals that are pregnant fall with all the other individuals that are pregnant in one big distribution, and we'll just kind of make some comparisons or figure out probabilities for whatever is asked. So for this one, they want the probability of being between 270, so x is between 270 and 280. And keep in mind, I did x, not x bar. This is just for an individual. That means we have to standardize. So this is the probability that Z is between 270 minus 266 over 16. That'll be less than Z, which is less than the same, only with 280. So 280 minus 266 over 16. And we'll get that probability, okay? I'm going to do this the quick way using, the features in your NSPIRE. So this will give us a normal CDF. Okay, from low is 270 to high is 280. Mean is 266. Standard deviation is 16. And this should look very familiar. This is going to be 0.2105. But they did ask what percentage. So we'll convert this to 21.05%, okay? So basically what they're saying here is about 1 in 5 pregnant ladies will have a gestation between 270 and 280 days, okay? Approximately. These are all approximations, but I guess they're pretty good. And this is not anything new. This is what we did in Chapter 5 way at the beginning of the year. All right. So at least how many days should the longest 25% of all pregnancies last? Again, this is not referencing any sampling. So I'm going to go ahead and I need to figure out, this is going to be, let's see, x minus 266 divided by 16 should be greater than or equal to some Z value where we have a 75, so that's 0.75 below, that'll be 0.25 above. So we do inverse norm, 0.75. And remember, 0.75, isn't that Q3? And we did have a Z-score at Q3 in a standard normal model. That's 0.6745. So greater than or equal to 0.6745. And you do the magic of your algebra, and you'll get x is greater than or equal to, let's see, 276.7918 days. All right? Now things are going to change. For letter C, it says, suppose a certain obstetrician is currently providing prenatal care to 60 pregnant women. All right. Now, there's way more than 60 pregnant women out there. All right. So that's a subgroup of that population. This is a sample. If you keep reading it, it'll become clearer. So according to the central limit theorem, describe the distribution of the sample mean, the average gestation period for this group. Clearly, this is a sample. So we're in a sampling distribution, so things will change a little bit. All right, so we're going to do a complete description. I am going to claim that this sampling distribution is normal, and I'm going to go with 2 reasons, although I only need 1. All right, my sample size is way over 30, so I have the central limit theorem to make it approximately normal. But what about up here where it says the population can be described by a normal model? Doesn't that make any sampling distribution that you could possibly have from that also be normal? All right. The mean, since this is an unbiased estimator, is going to be 266, just like up here, right? But your standard deviation has to be adjusted because you're not just looking at individual pregnant women, you're looking at groups of 60 of them, right? So this will be your original sigma adjusted by the square root of the sample size. Now you can also, if you want, you can use this straight through with your calculations, no problem. You can also do this. You can say it's normal with a mean of 266, and then you can just estimate by getting this down to a single number and rounding it. So you can say that that's 2.0656. All right, that's going to be close enough for us to answer part D. All right, but there it is. That's a complete description. So what is the probability, the mean duration of these patients' pregnancies? All right, these 60. Where does that sample end up being relative to all the other ones? All right, so that it'll be less than 260 days. So this is the probability that X bar, there's one change, is less than 260 days, right? So we'll standardize it because it's a normal model. So that's the probability that Z is less than 260 minus 266 divided by, and I could write this, but I'll just do it the long way, 16 over square root of 60. That's perfectly great. And I'm going to go old school with this, so I'm going to just get it to a Z-score. So it's the probability that Z is less than negative 2.9047. All right, and we'll just go ahead, since this is actually, a left tail calculation, it's down here, so it goes from negative infinity to that Z-score. So this is a normal CDF, and I'm just going to do negative 1,000 in place of negative infinity. That's good enough, up to negative 2.9047. Okay, and that gives you a probability of 0.0018. All right, not too bad. But I don't want you to walk away from this, because there's a key nuanced issue that I want you to really understand well. If you come back here and compare this to this, yeah, I got a probability of, my the mean duration of these patients' pregnancies will be less than 260 days. I have a probability answer that's remarkably small. Like that's 2 out of 1,000 or 2 out of 10,000 or something like that. 2 out of 1,000. That's really small, okay? But these are only 6 days apart. And what I asked the kids in class was, what if you just get a pregnant person, does it ever occur that some of them give birth 6 days earlier than the average or 6 days later? I mean, is that so uncommon that it would be 0.0018? So in other words, why is that so small? Well, the reason that it's so small is because we're not looking at individual patients here. We're looking at groups of patients. In fact, we're looking at N equals, if I can get that to right, N equals 60 patients. You've averaged 60 patients, right? What is the chance that most of these are going to average like preterm? That's really, seeing a few of them happen, just if we examine individuals, that's fairly common. But if we expect an entire sample of size 60 to average 6 days less, that's pretty rare. That we shouldn't really see that. That will only happen in 2 samples out of 1,000. So, yeah, that's why. Individuals, there's a lot of variability. You would expect to see a 6-day difference between what happens and what's expected. However, the average X bar being 6 days less for 60 patients, some of whom will be 6 days after, some days after 266, right? But to start seeing a whole bunch of them being, early for delivery is really unexpected. It's uncommon, right? That's the difference between what we did up here with just standard normal calculations out of a population where individuals fall, as opposed to where sample X bar values fall. And keep in mind one final thing, that if you have a sample of size 60, then your sampling distribution is way tall and way skinny and has almost nothing in the tails. That's why small differences show up as being unlikely to happen. So that's what I've got for you. So let me go ahead and have you work on these things. It's just the rest of them on this pages 6 and 7. And I'm going to call it a night, and I will see you tomorrow.